Myself, Dr. Rashmi Saxena, and I'm working in Government MH College of Home Science and Science, Jabalpur. In this lecture, we will discuss about effect of chemical exchange, deuteration, and stereochemistry as reflected in NMR spectrum. For recording the NMR spectrum, it is necessary to prepare solution. Usually 10% solution is prepared, and we use aprotic solvent for the preparation of solvent. The solvent available are carbon tetrachloride, carbon disulfide, deuterated chloroform, deuterated benzene, heavy water, and dimethyl sulfoxide deuterated, deuterated acetone, and hexachloroacetone. We can use neat sample also, provided that the sample is non-viscous, because non-viscous samples give sharp peak. If the sample is viscous, then it has to be diluted with any of the solvent. See the effect of solvent on the resonance frequency of hydroxyl proton. We know that the resonance frequency of hydroxyl proton depends upon the concentration, temperature, and the nature of the solvent. Table indicates resonance frequency of methyl and the hydroxyl proton in presence of different solvents. The different solvents taken here are deuterated chloroform, deuterated acetone, and deuterated dimethyl sulfoxide. In case of deuterated chloroform, methyl protons are more de-shielded as compared to hydroxyl proton because deuterated chloroform is a poor hydrogen bond acceptor. Hydrogen bond is not very strong. Whereas in case of deuterated dimethyl sulfoxide, we see that the resonance frequency of hydroxyl proton shifts to 4.01. That is, it is a downfield shift. Hydroxyl protons are more de-shielded here as compared to methyl protons. The signal is seen as 3.16. It is because dimethyl sulfoxide, it is a strong hydrogen bond acceptor, and strong hydrogen bonding takes place in presence of deuterated dimethyl sulfoxide. That is why the hydroxyl proton becomes more de-shielded. In case of deuterated acetone, the hydroxyl proton shows the resonance as 3.12 and the methyl proton shows the resonance at 3.31 delta value. Same effect of solvent on resonance frequency of hydroxyl proton is seen in case of ethyl alcohol. When the solution of ethyl alcohol is prepared in deuterated chloroform, then the signal for the hydroxyl proton is seen at 2.55 delta value, and the methylene proton shows the absorption at 3.65 ppm. And when the solution of ethyl alcohol is prepared in deuterated dimethyl sulfoxide, then hydroxyl proton becomes de-shielded and the resonance frequency becomes 4.33 ppm value, whereas the methylene protons shows the absorption at 3.45 ppm. That is, in this case, the hydroxyl proton is more de-shielded as compared to methylene proton, and it is because the dimethyl sulfoxide deuterated, it is better hydrogen bond acceptor, and in this presence hydrogen bonding becomes more strong, and that's why the proton becomes more de-shielded. It is the identical case as we have seen in case of methyl alcohol. This is a very interesting example to show the effect of solvent on resonance frequency. When chloroform solution is prepared in cyclohexane, then the proton of chloroform shows the absorption at delta 7.3 ppm. And when the solution of chloroform is prepared in benzene, then the proton of chloroform shows the absorption at 5.74 ppm. That is an upward shift. That is, proton becomes more shielded. Why this becomes shielded in presence of benzene. We know that benzene, it is electron-rich molecule and it behaves like a Lewis base. So chloroform forms a hydrogen bonding with pi electrons of benzene ring and it is held above the benzene ring. So we can think of here that the proton will feel de-shielding effect due to the hydrogen bonding. But the signal in presence of benzene is shifted towards the higher value, that is proton becomes more shielded. It is because benzene ring above and below experiences anisotropic shielding effect. So this proton is present in the diamagnetic area which is generated by the cyclically delocalized pi electrons. So the proton of chloroform becomes more shielded when its solution is prepared in benzene. Observe two NMR spectrum of ethyl alcohol. Spectrum 1 is recorded from commercial grade sample and the spectrum 2 is recorded from the pure sample. From the structure of ethyl alcohol, we expect here three signals. One signal because of the methyl proton, second signal because of the methylene proton, and the third signal because of the hydroxyl proton. In this NMR spectrum, we see a typical combination of a triplet and a quadruplet, and this shows the presence of ethyl group. But here, the signal from the hydroxyl proton does not couple with two methylene proton, which are present at the neighbor. And similarly, methylene proton does not couple with hydroxyl proton in commercial grade sample. But when the spectrum is recorded with the pure sample, then we see here that the hydroxyl proton couples with methylene protons and a triplet is seen. Similarly, methylene protons also couple with hydroxyl proton as well as methyl protons. So first, methyl protons couple with methylene proton and the quadruplet is seen. And it is J coupling, JCH2CH3. The value of J coupling is 8 Hz. Now, 4 lines of the signal again couple with hydroxyl proton and each line splits up into 2 peaks and this represents the coupling constant between JCH2 and OH and it is 6 Hz. Since the two coupling constants are different, overlapping of peaks does not take place and therefore in the signal of CH2 proton we get 8 lines and signal of methyl proton is a triplet here. So the question is why this happens? That in the commercial grade sample there is no coupling between hydroxyl proton and the methylene protons, whereas in the pure sample hydroxyl proton couples with methylene protons. This happens because of the rapid exchange of proton among the ethyl alcohol molecule, any alcohol molecule for that matter. So hydroxyl protons are labile proton and among the molecules hydroxyl proton is exchanged and the residence time of hydroxyl proton on oxygen is less than delta T. We know the equation delta T multiplied by delta V is approximately 1 by 2 pi. It is a constant. And delta T is the residence time of proton on any atom and delta nu is the coupling constant. So unless and until the residence time of proton is more than delta T, only then it will be able to couple with the neighboring proton. So in case of commercial grade sample, the exchange of proton is so fast that the residence time of hydroxyl proton on oxygen is very small. It is less than delta T. Therefore, the nuclear does not couple and there is no splitting in the commercial grade sample. But in the pure sample, the exchange rate is small and the residence time is greater than delta T. Therefore, the hydroxyl protons couple with methylene protons. These are the two NMR spectrum of methanol which are recorded at two different temperatures. First spectrum is recorded at 30 degrees centigrade and another spectrum is recorded at minus 45 degrees centigrade. And here also we see that the signal from hydroxyl proton is at 4.80 ppm value, but it is a singlet. It means it does not couple with the three methyl protons. And why it is not coupling with the methyl protons? Because of the rapid exchange of hydroxyl proton among the molecules. Similarly here, when the spectrum is recorded at minus 45 degrees centigrade, then the molecule is freeze and the rapid exchange of hydroxyl proton is not seen here. Therefore, the residence time of hydroxyl proton on oxygen is more than delta T and therefore the hydroxyl proton couples with three methyl protons and a quadrate is seen for the hydroxyl proton at 5.5 ppm value. And similarly, the methyl protons also couple with hydroxyl proton and a doublet is seen for the methyl protons at 3.35 ppm value. Rapid proton exchange is observed in carboxylic acid, amines, phenols and thiols. And this proton exchange is acid and the base catalyzed reaction. Therefore, if the sample is contaminated with any acid or base, then there will be very fast proton exchange and the residence time of the proton will be less than delta T and there will be no coupling between the neighboring protons. To see the neighboring proton coupling, it is necessary that the sample should be very, very pure. We can differentiate between primary alcohol, secondary alcohol, and the tertiary alcohol from their NMR spectrum, provided that the NMR spectrum is recorded from very, very pure sample. So primary alcohol, the neighboring proton will be 2 because the hydroxyl group is present on the primary carbon atom and the primary carbon atom will bear 2 protons. In the secondary alcohol, the hydroxyl group is present on the secondary carbon and the secondary carbon bears only 1 proton. In tertiary alcohol, the hydroxyl group is present at the tertiary carbon atom and there is no proton present at the tertiary carbon atom. Now look at the signal given by hydroxyl proton in case of ethyl alcohol. Here, the signal of hydroxyl proton splits up into 3 peaks because of the neighboring 2 methylene protons. So by looking at the NMR spectrum and observing the splitting pattern of hydroxyl signal, we can predict that this is a primary alcohol because in the primary alcohol, the hydroxyl signal will split up into 3 peaks. It will be a triplet. Similarly, in case of secondary alcohol, the carbon atom will bear only 1 proton, so the hydroxyl peak will show a doublet. And in the tertiary alcohol, the hydroxyl signal will be a singlet. So if the NMR spectrum shows the triplet for the hydroxyl proton, it is a primary alcohol. If the signal of the hydroxyl proton shows a doublet, it is a secondary alcohol. If the signal of hydroxyl proton, it is a singlet, it means that the alcohol, it is a tertiary alcohol. Hydroxyl proton, acidic proton, and proton present on nitrogen, they are known as labile protons. They are known as labile protons because they can be exchanged by deuterium. So when alcohols are treated with deuterium oxide, then hydroxyl proton is replaced by deuterium and we get ROD and HOD. So the signal for the labile proton will be absent when the spectrum is taken out in presence of deuterium oxide. Similarly, acids when treated with deuterium oxide, then acidic proton is replaced by deuterium and the signal from the acidic proton will be absent when the spectrum is taken out in presence of deuterium oxide. So this is a very good method to verify that the particular signal is given by a labile proton. This method is also used for identifying the active methylene protons. Active methylene protons are those which are present in between two carbonyl groups. So active methylene protons are highly acidic protons. So they can also be replaced by deuterium when it is treated with deuterium oxide. So methoxide is taken, that is a base is taken, and a small quantity of deuterium oxide is added when active protons are replaced by deuterium. So the signal from the active methylene protons will disappear in presence of deuterium oxide. So this is a very good method for verifying the presence of labile protons. We know that the carboxylic acid proton, it is a labile proton. And when the NMR spectrum of an acid is taken out in presence of deuterium oxide, then there is a rapid exchange of acidic proton with deuterium. Therefore, in presence of deuterium oxide, the NMR spectrum of an carboxylic acid will not show the signal because of the acidic proton. Now, if we wish to distinguish between aldehyde proton and carboxylic acid proton, then this concept can be used. Because the aldehydic proton and the carboxylic acid proton shows a signal at 9 to 12 ppm value. If we wish to confirm it, then the NMR spectrum is taken out in presence of deuterium oxide. If it is an acid, then the signal because of the acidic proton in presence of deuterium oxide will be absent. And if it is an aldehydic proton, the signal will be there in the NMR spectrum. Therefore, by use of deuterium oxide, we can confirm the presence of acidic proton. This is a diphenylbutane molecule. Careful observation of this molecule indicates that this molecule has a C2 axis of symmetry. That is, if it is rotated by 180 degrees, then the proton A and B are interconvertible. And also it has got a plane of symmetry. So proton A and B are interconvertible by plane of symmetry also. So these two protons are equivalent protons and they are known as the homotopic proton. And they cannot be distinguished by NMR spectrum. So these two protons, homotopic protons, are equivalent protons in chiral and achiral medium. 3-methyl protons of toluene are homotopic protons. They are interchangeable by rotation at the axis C4, C7. And the rotation is done by 120 degree, that is a C3 axis of symmetry. Rotation is very rapid and therefore an average environment is created around these 3 protons, and these 3 protons show the absorption at the same frequency. If the molecule is frozen, then average environment will not be there around these 3 protons. They will feel the different environment. One proton is present below the plane of the ring. Proton with 1' is present above the plane of the benzene ring, and the proton with double prime, it is present in the plane of the benzene ring. But these 3 protons cannot be distinguished because of the rapid rotation around the axis, and therefore all the 3 protons shows the absorption at the same frequency. 2 methylene protons of benzyl alcohol are anisotropic protons. There is a plane of symmetry passing through OH group, and these 2 protons are interconvertible by plane of symmetry sigma. These 2 protons are equivalent protons and cannot be distinguished by NMR. When they are present in the achiral solvent, they are equivalent proton. In presence of chiral solvent, these two protons become non-equivalent proton and they will show the absorption at different frequencies. This is cyclobutanol molecule and this shows the presence of distereotropic protons. Distereotropic protons are those which are not interconvertible by rotation or by reflection. Carefully observe cyclobutanol molecule. There is a plane of symmetry passing through carbon number 1 and carbon number 3. So, due to this plane of symmetry, protons present at carbon number 2 and carbon number 4, they are enantiotropic protons. So, 2 proton Hc are enantiotropic protons, 2 protons D are enantiotropic protons, but C and D protons are distereotropic protons. Similarly, 2 protons which are present at carbon number 3, E and F, they are also distereotropic proton. Therefore, this compound will show 6 signals in the spectrum. One because of the hydroxyl proton, second because of the proton which is present on the same carbon atom on which hydroxyl group is present. Then one signal because of C protons, another signal because of D protons, one signal because of E protons, another signal for F protons. So in all there will be 6 signals in the NMR spectrum of this compound. Now see the chlorocyclobutane molecule. This molecule also shows a symmetry, plane of symmetry passing through carbon number 1 and carbon 3. And therefore, protons present on carbon number 2 and carbon 4, they are enantiotropic proton. So proton A are enantiotropic, proton B are enantiotropic, A and B are distereotropic, then E, D, they are distereotropic protons. Therefore, this compound will also show 5 signals. This is cis-1,2-dibromocyclopropane and this compound shows 3 signals. One signal because of proton A, second signal because of proton B, and the third signal because of proton C. Proton A and B are distereotropic protons and proton C are enantiotropic protons because there is a plane of symmetry passing through carbon number 3 which makes proton C enantiotropic protons. So when proton A is substituted by deuterium, then we get the products 2, and when proton B is substituted by deuterium, then we get the product 3. And these two products are distereoisomers. Therefore, proton A and B are distereotropic protons. Two geminal protons in vinyl chloride are distereotropic protons because they are not interconvertible by rotation or by reflection. Therefore, this compound will show 3 signals in the NMR spectrum. This is citric acid. In citric acid, there is a mirror plane symmetry passing through carbon number 3. And due to this mirror plane symmetry, proton present on carbon numbers 2 and the protons present on carbon number 4, they become enantiotropic proton. So proton A1, A2 are enantiotropic. Protons B1 and B2 are enantiotropic protons, but proton A and B are distereotropic proton. There will be 5 signals in the NMR spectrum of citric acid. One signal will be because of the hydroxyl proton. Second signal will be because of the proton which is present on the same carbon atom on which hydroxyl group is present. Third signal will be because of the acidic proton. Fourth signal will be because of A proton and the fifth signal will be because of B protons. So proton A and B are distereotropic protons. They are not interconvertible by rotation or by reflection.